This video is about linear approximations. And so if we, this is how they came about, okay? If you consider some function f, so I'm just going to draw some function f here, okay? There's some function f. And we consider the tangent line at some point a. So here's some point on the x-axis. This is the x-axis, and this is the y-axis, or f of x. And this is some point a. Okay. If we go up to the function, oh, I made that so linear. Let me draw a new function. I want this not to be so like that. What if it's curvy or something? Maybe I make it more curvy or something. Okay, at a is here. All right. So we know that a tangent line approximation of the point, a tangent line right there would look like something like that. Okay. So we are familiar with a function and its tangent line. So we've seen that when you take the tangent line of a function at a certain point, those points of the function and that point of the tangent line are the same point, right? At this point, a and f of a are a part of the function, and they're also equal to the tangent line approximation. That point is equal. But also, for points that are very close to a, the tangent line is not equal, but it's very close to the actual y value of the function f. So for values that are close to a but not exactly a, we can get a pretty good approximation by just taking the value at the tangent line instead of f. So the idea of linear approximations are that sometimes it is difficult to calculate the exact value of a function at a value close to a. So, in those cases, we settle for an approximation, the linear approximation of the value. Instead of getting the exact value, it's like this approximation is so close and it's so much easier to calculate, we're going to use the linear approximation. So that's the idea behind it. So let's recall, like, how would we even calculate this tangent line right here? Okay, well, tangent line, right, it's based off of this point slope form. Y minus y1 is m times x minus x1. This is the formula of a line that you've seen all the way since intermediate algebra. So you can say, well, this is equal to y. If I add y1 to both sides, I get this. All right, now let me bring the calculus in. For tangent line, what is the slope at the tangent line? Well, we know that the slope, m, is f prime of a, if it's at the point a. And if we want this at this value a, what is x1 and y1? Well, x1 and y1 are a f of a, right? And so f prime of a is the slope at this line. So if we write this in terms of the point a, y, or what we're calling the linear approximation, is equal to, oh, this is not a, what is this? This is supposed to be a plus sign. I'm sorry. 2 equal signs. That's crazy. Okay. F1 is f of a plus the slope f prime of a times x minus a. So this is the equation of the tangent line at the point A, but now it's also known as the linear approximation. So I'm about to show you how this works. we have a few blanks on this worksheet, and so it says the blank approximation of a function line, and so what goes here is the linear. When we plug it in the equation of the line, linear, instead of using the actual function, the linear approximation of a function f at a value a, it's also called, or the tangent line approximation of a function f at a is called the linearization of a function f at a. And so the linearization, L of x, this is another way of rewriting this equation of a line, is equal to y1, which we're calling f of a, plus m, which is f prime of a, times x minus x1 times x minus a is how we write it. This is the linear approximation. So how does all this work? We're about to have a look at that with this example 1. So in example 1, it says find the linearization of f of x equals to x plus 3 at a is 1. Use it to approximate the numbers the square root of 3.98 and the square root of 4.05. Are these approximations over or under estimates? And then it says for what values of x is the linear approximation accurate to within 0.5 or within 0.1? And then I have this little note I'm going to talk about. So basically, there's 3 parts to this. The first part, it says to find, first we have to find the linearization of f of x at equals to x plus 3 at a is 1. All right, and so that's the first thing we're going to do. Here we go. Well, the linearization is just the equation of the slope of the tangent line when a is 1. We are past learning the definition of the derivative, and we can use the derivative rule. So let's first find, we've got to write the equation of a line, we need a point and the slope. What is the point? Well, the point is a f of a. All right. So our function is f of x. So, and what is the value of a? They told us it's 1. So 1 f of 1. So x is 1. F of 1, I'm going to put in 1 into this function. It's going to be 1 plus 3, which is the square root of 4, which is 2. So a f of a is 1, 2. This is our x1, y1. What is the derivative of f of x? Well, f prime of x, this is really, if I think of f of x, which is the square root of x plus 3, as x plus 3 to the 1/2 power, then f prime of x, you can use power rule. It's 1/2 times x plus 3 to the negative 1/2. And there's a little bit of chain rule in here because this was not just x, it was x plus 3. But the derivative of x plus 3, the derivative of x is 1, the derivative of 3 is 0, so it would be times 1 plus 0 or 1. So this is really the whole derivative. I can write it like this, 1 over 2 times the square root of x plus 3, because this is a negative power pushing it down to the denominator. So what is the slope? Well, the slope is where we're f prime of a, but a is what? It's 1. So f prime of 1 is 1 over 2 times the square root of 1 plus 3 is 1 over 2 times the square root of 4 is 2 is 1/4. And that's right, the equation of the line. It's y equals 2, but I'm going to write it as a linear approximation because this is the notation. I'm using it to approximate something. L of x is equal to f of a, which is this y value here, 2, plus the slope, 1/4 times x minus a, or x minus 1. So I can simplify this linear approximation. This is 2 plus 1/4 minus 1/4. Oops, I need my x right there, which is equal to 1/4 x plus 7 over 4. If I get a common denominator of 4 there, that's going to be 8 minus 1, 7 over 4. So this right here, this is the linear approximation of the function square root of x plus 3 at the value a is 1. So that right there is the first part of this equation. We found that. That's this part. Okay, then they say, Well, let's do something with this. Let's use it to approximate the numbers. This is the second part. Use it to approximate the numbers, the square root of 3.98 and the square root of 4.05. All right. Well, this is what we're going to do. We're going to think about if we're going to use, okay, for the square root of 3.98. Let's think about this. What is the value of x? So they want us to approximate this. Instead of putting in 1, we're going to put in 0.98 for x so that we can find the square root of 3.98. So in this case, x is equal to 0.98. So all I do is I plug in, this is my linear approximation, L of x, or L of 0.98, is equal to 1/4 times 0.98 plus 7 over 4. And so this is equal to, when I plug those numbers in, I get 1.995. So what this is saying is that by using the linear approximation, we found out that the square root of 3.98 is very close to the value 1.995 using the linear approximation. All right, let us go ahead and try it for the square root of 4.05. Okay, x is not equal to 1, but it's equal to something close to 1, just like it was 0.98 was something close to 1, right? 4.05, what would x have to equal to if we were going to try to evaluate this? Well, 3 plus what would give us 4.05? In this case, x has got to be equal to 1.05. So the value of x is not 1, but it's close to 1. So this estimate is going to be pretty good. So let's evaluate that. What is L of 1.05? We're going to plug this in. It's 1/4 times 1.05 plus 7 over 4. And this gives us, this estimation, this approximation equals to 2.0125. 2.0125. That's what the linear approximation equals to. So what we're saying by this is that we've estimated that the square root of 4.05 is approximately equal to 2.0125. Now, here's the second part of this. Are these approximations? So this was use it to approximate this. This was this. We just did this part. Approximate these. Right here, this is our approximations. Now they're asking us, are these approximations over? Let's do this part. Are they over or under estimates? I'm going to use my calculator and we'll have a look. So by calculator, using my calculator, if I take the square root of 3.98, it gives me more digits, more accuracy. It says I get that the square root of 3.98 is approximately equal to 1.994993734. Is my linear approximation an over or an under estimate? This is a little bit bigger, so it's an over estimate. All right. Let's compare it with using calculator. Using my calculator, I get the square root of 4.05 is approximately equal to, let's do this, square root of 4.05 gives me 2.012461118. And so these are pretty close. It's good if I round to the 1, 2, 3, 4th place, it's going to be spot on, but this is this is closer to accuracy. So this is smaller than what my linear approximation. So this is a bit of an overestimate. All right. there are some pictures in the book. This example is from the book in this section. So you can see pictures where they drew the tangent line, and you can see why it might be an overestimate. They have some nice pictures there. But let's deal with this last part. Now, this last part is something I just want to show you what's going on. You do not have to do that. So I put this little note here that says in section 310, homework problem number 9, I have assigned that. But there's a part of the problem that says find the accuracy to within 0.1. I'm about to show you how to do that, but you do not have to do that part of the problem. You may omit that part of the problem. So you don't have to do that. But I do want you to understand what they're asking you and what that means. So I'm going to do it for this one. So you can just see this is the last part. And mostly I'm asking you not to do it because I said you didn't have to use a graphing calculator, and I'm going to be using my graphing calculator for this. So but I want you to understand the concept of accuracy. So accuracy, we want to see how accurate our estimate, our approximation is compared to the exact value. So to do that, you say, let's find the absolute value of the difference of the actual minus the approximate. So when you subtract something, it's the difference between two. And we want this to what accuracy? We want it to be less than 0.5, or we could set it up again so that it be less than 0.1, depending on how accurate you need to be. So this is what this looks like. The actual in this case would be, I think I'm about to run out of lead. It would be the square root of x plus 3 is the actual minus the approximate is our L of x. 1/4 x plus 7/4. We want this difference to be less than 0.5. Okay, just if you go way back to intermediate algebra, you learned hopefully that the absolute value of x when it's less than a, to remove the absolute value sign, you could set up this inequality. Negative a is less than x is less than a. So I'm going to do that here. I'm going to remove the absolute value signs, and this is going to be negative 0.5 is less than the square root of x plus 3 minus 1/4 plus x plus 7/4 is less than 0.5. So what I decided to do was graph this. And then I'm going to set up y in my calculator. I'm going to write y equals to this value and see where it intersects. And that's going to tell me the value of x that I have to stay bounded by. And I'm going to do the same thing here. I'm going to set this up. This is going to be my y1, and I'll try y2, and I'll try y3 in my calculator. So if I do that, I have already put y1 in my calculator as this middle part. This is y1. And I'm just going to tell you what happened. When I put in, let me call this one y3. When I put in y equals to 0.5, I found that there was no intersection. So this one did not have any bearing on the problem. But when I put in y is negative 0.5, I want to see where they intersect. And that's going to tell me the two x values I need to stay between in order for my linear approximation to be accurate within 0.5 values. So I put y1 is this, y2 is this, y2 is 0.5, and I'm going to graph it. And so let me quit this, and let me see. Let me graph. Oh, it's already graphed. So let me remove one of these so you can watch it come up. I want you to see it come up. First, let's graph this middle part. And the window I am using for this, in case you want, if you have one of these and you want to replicate this problem, the window I chose to use for this is -5 to 10 scale by 1 for x's and -10 to 10 scale by 1 for y's. All right, so that was y1. Now I'm going to go to my y equals screen, and I'm going to put in the second graph, -0.5, and I'm going to graph them both on the same screen, and then that's what they look like. All right, so This is just to find out the accuracy. So I'm going to do second calc and see where they intersect. I'm going to go to 5, and it intersects it at 2 places. So I'm going to go over here to the left, and it says, I'm on my first curve, and then I hit enter, and it toggles to my second curve, and it says, do you want me to find this? Do you want me to guess? And I'm like, yes. And it tells me that x is equal to negative 2.656854. All right. Then I want to find the second intersection place, so I do second quit. I go to calculate. I say choose 5 to intersect again, but it already found that one. I have to move my cursor closer to the second point of intersection. So I've hit enter, and then I'm going to hit enter. It's going to go toggle to my second curve, and then it says, do you want me to guess? And I say yes, find the intersection, and it found the one over here, which is x is 8.65685. So as long as I choose x values that are between negative 2.656 and 8.656, if I want to use this linear approximation, so I'm going to round this, negative 2.65 and 8.65. I round it in a way that would keep me safe, that it's totally within a good area to choose from. As long as I stay between these two values of x, whatever I choose to put in here for my linear approximation for x, as long as the value of x is between these values, I will get a decent to within 0.5 margin of error approximation for values of this function. Now, if I want it to be not 0.5, but if I change this number to 0.1, I can do the same thing I just did with my calculator, and I found that when I did this, I need to stay a bit closer. I can only go out to negative 1.1 and positive 3.9 if I did that same exercise for if I wanted better accuracy. I couldn't go as far out. Okay, that is an illustration of accuracy. You don't have to do that on your homework, but now I want to do the second example. So to make sure you understand some of the language they're using. So example 2 says, let me see if you can see this. Yes, you can. Okay. So example 2 says, use a linear approximation to estimate this 1 over 4.002. Is this an over or an underestimate? So basically, I want you to understand how to approach this problem. What they're asking us to do is to use a linear approximation. What is a linear approximation? It's this. It's the tangent line, right? So L of x is equal to y1, which we're now calling f of a, minus m times x minus x1, but our slope is f prime of a times x minus a. This is our linear approximation in general. First, we got to ask ourselves, well, what is the function, f of x? What are we trying to figure out? They just gave us this value. Well, the function, and so you have to back out of this for a moment and say, well, what could a function be? 1 over x could be a function. And then what would be the value of a? 4 would be the value of a that I could use to find a linear approximation. And then I could say, well, 4.002 is close to 4, so I could use my linear approximation to figure out this value. So this is not immediately obvious what you're supposed to do with this when they say find a linear approximation, and you do have some homework problems. So first, you think of a function that could fit this pattern, 1 over x, and then you find an a value that would be close to what they're trying to ask you to do. So let's proceed. Let's write the equation of the tangent line of this function at this point. So we need the point a, f of a. All right, well, a is 4, and f of a is 1 over 4. So that's 1 over 4. All right, so we found this, and we found this. Now, to find f prime of a, we take the derivative. So f of x is 1 over x, and I'm going to think of it as x to the negative 1, because that's easier to take a power rule derivative. So f prime of x is negative x to the negative 2. All right, Now, if I want to know f prime of a or f prime of 4, I'm going to say this is negative, which we can think of this as negative 1 over x squared. I'm going to think of it like that. This is negative 1 over 4 squared. So negative 1 over 16 is what the slope is. Let's write our equation, our approximation. L of x is f of a, which is 1/4, minus the slope, which is negative 1/16, times, why did I have a minus there? This is a plus. F of a plus this, I don't know why I put a minus. F of a plus f prime of a, the slope, times x minus a, which is 4. So I want to make sure I didn't do that in other places. That's okay. This should be a plus. I'm sorry about that. So now we can simplify this function. The linear approximation is going to be 1/4 minus 1 over 16x plus 4 over 16. If I just add these numbers together, 1/4 and 4 over 16, I get that the linear approximation is negative 1 over 16 times x plus 9 over 16 is what I get when I add those together. Is that right? 9? No. Let's see. Times 4 is 4 plus 4 is 8 over 16, and 8 over 16 is just 1/2. So this right here is the linear approximation for the function 1 over x at the value a is 4. So since 4.002 is close to 4, we can use this as an approximate way of finding the value of the real function 1 over 4.002. So let's do that. L of 4.002, you can just put this straight in there for x, is equal to negative 1 over 16 times 4.002 plus 1/2. So that ends up being, when I put that in, my linear approximation ends up being 0.249875. They want me to say, is this an overestimate or an underestimate? So I can use my calculator again and say, well, what would that actual value be? 1 divided by 4.002 is, by calculator, 1 over 4.002 is 0.249875065, and I believe it goes on, but I just only have this many places on my calculator. But is this an over or an underestimate? Well, this truncated at 5, and this has more numbers after it, so this is an underestimate in this case. But it's pretty close, all the way out to 5 digits. No, 6 digits. 1, 2, 3, 4, 6 digits. All right, so that's that. I have one other thing I wanted us to do, which I didn't put on the sheet, but it was to, if we were to draw, I'm going to draw the function. I'm going to put the function in my calculator, 1 over x, and then I'm going to put the tangent line in my second graph. It's going to be negative 1 over 16 plus 1/2, and I just want to look at the function in the tangent line and see if it's close at 4, which it should be. So we'll see how much this is. So if I put in my y1, this one's not color. Maybe I should just do it real quick in the color so we can see it. What window did I use there? For this window, I'm using negative 1, x is negative 1 to 5, and then I'm going to do it by a scale of 1, and then my y is going to be from negative 1 to 1, and I'm going to take this by 0.1. And so I didn't automatically know to do this. What I did was I've already graphed this, and I figured out what's going to give me a really good viewing picture. So I'm going to do second quit, and now I'm going to go plug in my functions. I'm going to clear this guy off and clear this guy off. And so what I want to do is put in 1 divided by x for my first function. That one's going to turn up blue. And my second one I keep forgetting my slope there. My x there. Y2, I want it to be the linearization. So it's going to be negative 1 divided by 16 times x. And then plus 0.5. And I'm going to graph this. First, going to come up my function 1 over x. And second's going to come up my tangent line. And so we're looking at 1, 2, 3, 4. You can see that it's pretty close right there. And you can see for values to the left and to the right of my function x, it's pretty close. It's right on there. So that's a pretty good approximation. All right, applications. Why do we even do this? Sometimes it's hard to find the exact value, and one of the major applications is in physics. This is just a sheet I was using to make sure I stayed on the screen. Linear approximations are used often in physics and engineering applications. A good example of this is when they're finding the theory of optics, they use linear approximations in the design of lenses for optics. And there's many other applications, but just so you see that there's a point to this. All right, that's it.